option of moving from grey to green hydrogen for these very difficult, hard to abate sectors. There are some other very interesting options for India to use green hydrogen. India has announced the national logistic policies. This is a wonderful AI-based platform, a hub and spoke model, where from port to last mile delivery, the freight is going to move around the large freight transportation corridors that are being constructed today. For example, Mumbai, Nagpur, the Samruddhi Mahamarg is one of those. Okay, and so there are these large infrastructure that has been built, and a high-tech AI-driven mobility transportation policy has just been announced. Now, if you couple that with hydrogen, it looks very interesting, because you can take very large trucks, smaller numbers but larger trucks moving over longer distances, and that is exactly the use case where hydrogen beats everything else. So if you marry the national logistics policies with the green hydrogen mission, I think that's quite a winner. You can do the math and check this for yourself, and we've done it. The other interesting thing is India has about 100 islands around it, and some of them are very strategically placed. For example, the Great Nicobar Island is something that India is developing as a strategic location. It's right at the shipping lane, one of the most populous shipping lane. And today that kind of islands are supported by diesel, right? The electricity energy there is supported by diesel, which is transported from the mainland. Imagine if you were to create renewable energy parks there, create hydrogen, bunker hydrogen, and use it for ship transportation. It's something that will compete against Singapore, which is just across the strait. So there are these interesting options available for India, and I hope we look at it more carefully. Lot of states have kick-started the hydrogen growth. Kerala is the leader, but almost every other state, including Maharashtra, has announced green hydrogen policies. There are many smaller but pilots, successful pilots that have already been demonstrated in the country. So I think the excitement is really growing here, and not just the public sector, but the private sector is also investing very deeply. We are going to look forward to Siddharth talk about how his company is investing into hydrogen, but a huge amount of interest from the corporate sector is also being shown in this domain. I want to end by this last slide, just to give you a feel for what it means to even convert the first 5 million tons of hydrogen, right? Just to get to a sense of reality here. To make 5 million tons of hydrogen by electrolysis, and that may not be the best route to make it, but suppose you want to make everything by electrolysis, you would need 32 gigawatts of renewable energy. You would need 300 million liters per day of RO water. Now that 32 is an interesting number. It's about 25%. No, what is that? 20% of the renewable aims that we have for the country. So it's not very large. The 300 million liters of water per day looks like a very large number, but actually it is not. The entire Chennai city is supported today by 3 large RO plants. One of them, which is the largest in India, is already producing 100 million liters per day of RO water, right? So it's not a very large number. I did talk about large renewable electricity required, about 120 gigawatts required to support the 32 gigawatts of electrolyzer. But along with it, huge amount of storage is required, because all of that sun, wind are not available 24/7. So it's not just sun and wind, it's a huge storage requirement for it. And that's a very large capex, about $150 billion of capex would be required to set up something like that. A lot of land is required, but that's not very large. It's 0.1% of India's land mass. But if all of this is done, we are looking at, just by producing this 5 million tons of hydrogen, you are looking at abatement of 30 to 40 million tons of CO2. That's not a small number. And it also means saving foreign exchange to about 60,000 crores. And that's the reason hydrogen seems very interesting. The numbers look daunting, but actually they're not as daunting as they might sound. The real elephant in the room is the levelized cost of hydrogen, and Professor Yadav mentioned about anything less than $3 per kg starts making hydrogen very interesting. How do you get there, right? So today, if you have power available to your doorstep at 4 rupees a unit, if you design your electrolyzer plant carefully, by sizing it carefully so that you have an integrated utility park and electrolyzer together, it is possible to reach $3 per kg even today, okay, but under those conditions. And now you add scale of manufacturing, you add indigenization, you can cut another $0.8 per kg, you add technology upgrades, move the efficiency by another 2-3% up, your capex starts to go down. And so it's possible to shave off another half a dollar or $1 from that $3 and hydrogen then starts looking extremely attractive. But there are lots of ifs and buts in this, and the country has to take a risk of or a bet on scaling up electrolyzers, scaling up biomass based hydrogen in order to hit that less than $3 per kg of hydrogen at the user level. For sugar industry, you can have multiple routes from sugarcane, let's say producing electricity, selling electricity, which is what is done today. Instead of that, if you convert that electricity into hydrogen, you can today get a lot of margin because the merchant sale price of hydrogen today is anywhere between 400 to 800 rupees a kg of hydrogen. So there's a lot of margin available. So instead of selling electricity, selling hydrogen might look very interesting. But what Professor Yadav mentioned was the turquoise hydrogen. That is even more interesting because you can take biomass, pyrolyze it to make graphene, and if you can make the right quality carbon, not just graphene, any right quality carbon, there are many interesting applications. In fact, the lowest application for that carbon is in the tire industry, and that itself fetches you a lot of price for that carbon. Hydrogen itself has a good price as well. So these are all interesting options that are available today. So I'm going to stop here. There are many slides, but I'm going to skip all of them because I'm too mindful of time. And I think all I want to say here is that hydrogen is coming up to be an exciting option for the sugar industry. There is many things that are possible in the domain of hydrogen, and I hope that as the country moves into more renewable energy and less carbon emitting forms of energy, hydrogen will play a critical role as one of the clean energy transition vectors. Thank you very much for your attention.
Recently living or living organisms is essentially I am talking about. So how do we valorize that? So trees, crops, municipal solid waste, animals, all of that come, even industrial waste containing carbon, wastewater treatment, wastewater containing carbon, all of that, how do we valorize this? So the focus is valorizing the carbon in all these waste streams. That's the focus of this stuff. And I'm not going to talk about what is circular economy. Professor Yadav has nicely introduced the recycle, reuse and all of that. So I'll skip that and we'll directly jump towards valorizing biomass and what do we need to do. Professor Yadav and Dr. Ashish Lele have talked about variety of process pathways, and indeed biomass is a complex chemical substrate. As Professor Yadav said, it is a mixture of hemicellulose, cellulose and lignin. Even in other biomass sources including MSW will have very different kinds of complex chemicals, and obviously there are variety of valorization pathways, right from thermocatalytic, biochemical are the broad divisions, but even thermocatalytic there can be gasification, pyrolysis and so on and so forth. Today I am going to restrict my talk to biochemical pathway, and even there I am particularly focusing on biomethane rather than on bioethanol or other products. My collaborator from the project, Nigel, will probably talk about later on butanol as a product from the biomass, but my talk I am going to restrict it to biomethane or bio-CNG essentially. So what are the key issues there? And how do we select the pathway? Right? There are several pathways. So essentially, the best pathway need not be selecting the highest price product, right? Because eventual overall effectiveness of the pathway depends on what is the yield of the product, what is the price of the product, and what is the cost to conversion of this product. Right? So that dictates the best pathway. It also depends on these. The selection of pathway also depends on where you want to implement the path, right? So if our interest is to implement the valorization in the rural areas, you need to ensure that the kind of pathway which you select for valorization is suitable for implementation in the rural areas. Maybe I don't need that. Can you hear me at the back?
No. Please use the mic.
Better you can go for
Vivek, you can use
Okay,
this.
yeah.
You can use this.
That's fine. Okay, that's fine. Right, so I was talking about selecting the pathway so that we know that it is appropriate for the intended application. And that's why we have selected anaerobic digestion particularly. So anaerobic digestion has been used for several decades. You need to put this on. Okay, that's fine. Thank you. Yeah, so I'm going to focus on anaerobic digestion, and as you can see here, anaerobic digestion is not a new process. It is anaerobic fermentation. There is no specific strain of microbes is used. Typically, consortium of microbes are used. So in a way, that is quite robust. It can handle variety of feedstocks. That's the goal. Traditionally, anaerobic digestion processes are very slow. First of all, consortium of microbes are used, and they are fed with whatever raw material, whatever waste biomass you can get your hands on. And most of the times, typically, they are fed without any pre-treatment. Efforts for optimizing anaerobic digestion or efforts for intensifying anaerobic digestion are relatively recent phenomena. Right? So that's why, in fact, anaerobic digestion, though it has been practiced for a long time, it has also attained some notoriety in the sense those are slow processes, those are huge reactors. Typical anaerobic digestion reactors are like 8,000 meter cube reactor. So compared to our chemical reactors, those are really huge reactors. Why? Because processes are very slow. And that is where we decided to focus on. So as I said, while I was at NCL, I never worked on biomass, and I decided to take a fresh look and started working on biomass and anaerobic digestion. That was an opportunity to rethink and relook at with a fresh perspective on what is happening in anaerobic digestion, right? And then we decided to focus specifically on two aspects. We specifically focus on pre-treatment of feedstock so that we improve the digestibility, and we also decided to use chemical reaction engineering models so that we can optimize the reactors. In this particular slide, I am showing you variety of options for intensifying anaerobic digestion. Some of these are quite well known in biotechnology area. What we decided to play with our strengths of chemical engineering, and we implemented some of these traditional conventional ways of improving performance, and particularly focused on the pre-treatment as well as chemical reaction engineering models so that we can improve rate of digestion as well as yield of digestion. Okay. And I've listed some of our intensification strategies here, and primarily we'll talk about pre-treatment and modeling, and maybe touch upon a couple of intensification strategies which probably still need further development. So what is pre-treatment? So this is typically for people familiar with anaerobic digestion. This plot shows biogas generated, cumulative biogas generated versus time, right? And the goal for pre-treatment is to improve this. I don't think this pointer is working, but the goal basically is to increase the biogas yield or biomethane yield per ton of feed, as well as increase the rate of digestion. So there are twofold objectives: increase the yield of biogas per ton of feed, and increase the rate of digestion, so that for the same digestion you can increase the throughput and the yield. Right? Again, there are a variety of different pre-treatments. I'm going to focus on hydrodynamic cavitation. I'm not discussing why we have arrived at. We did critical analysis of variety of different pre-treatments, right from biological pre-treatments to chemical pre-treatments, and eventually arrived at a conclusion that from the process and techno-economic perspective, hydrodynamic cavitation, which is a physicochemical pre-treatment process, is the most optimum pre-treatment for anaerobic digestion. Some of you are familiar with hydrodynamic cavitation. Just one slide introduction to cavitation. Essentially, we generate low pressure in fluidic devices. At that low pressure, tiny amount of water gets evaporated and form these bubbles or cavities. When these cavities travel to high pressure region, these cavities or bubbles collapse and generate very intense local hotspots. It also generates very intense turbulence. It also generates hydroxyl radicals. And essentially these hotspots and intense turbulence break the particles. So you have biomass. Typically biomass will have solid particles suspended in liquid in a slurry. You need to break those particles, physically break those particles, so that you improve the surface area of interaction. Plus hydroxyl radical also causes depolymerization of long chains. So typically, as Professor Yadav mentioned, lignocellulosic biomass is polymers, complex polymers of lignin, cellulose and hemicellulose. So these are complex polymers of C5, C6 and C7, C8 compounds. So these polymers are difficult to digest. So hydroxyl radicals will cleave those long polymer chains and create depolymerization. So twofold effects. Hydroxyl radical will chemically depolymerize those long chain polymers, and high shear and high turbulence generated will physically break those particles. So essentially you increase the rate of digestion as well as the yield of digestion. There are a variety of cavitation devices. So using cavitation for pre-treatment is also not a new idea developed by us. That has been proposed by some academic papers. The real problem was none of those were really implemented in practice, mainly because of these two reasons, right? Broadly speaking, all the cavitation devices could be can be classified into these two parts. One involving small holes. None of those none of those devices are useful for treating biomass because they will immediately clog. The other devices were having moving parts with a rotor stator. So those are obviously, they can handle solids, but those are expensive. And in all these devices, cavitation occurs very close to solid surfaces, and therefore it erodes those solid surfaces. Effectiveness comes down. And in fact, early deployment of hydrodynamic cavitation has therefore generated a lot of bad name. Many people thought that hydrodynamic cavitation is not really useful because the effectiveness quickly reduced. So what we did, and the origin of this invention is at NCL. I'm glad to say that NCL director is here, and we in fact we could license this innovation and know-how to our startup company. What we did here is, in our hydrodynamic cavitation device, we combined the good points of both these types of devices. So we don't have small holes, so there is no danger of clogging. But we use the rotational flow of advantages of rotational flow of the other rotor stator type of devices, but without any moving parts. The most important advantage here is all solid parts are shielded from the cavity damage. So there is no erosion, no small holes, so no clogging. There is an early inception. So most of the boxes which people were talking about as disadvantage of hydrodynamic cavitation, we could in fact mitigate them by designing these novel devices. We developed detailed computational fluid dynamic models right from the collapse of the cavity to device scale to scale up. We also use machine learning for complementing the physics-based computational fluid dynamics models, so that some of these unknowns of biomass, we could actually use the data-driven models to complement our physics-based models, and we have now full toolkit which will allow us to simulate influence of pre-treatment on a lab scale to full plant scale. Right, so that's the advantage. Both these advantages helped us to overcome some of those disadvantages of hydrodynamic cavitation and the bad name which hydrodynamic cavitation had earned. In order to increase the utility of that pre-treatment, we also developed detailed reaction engineering models. Again, our chemical engineering background was useful. Traditionally, the biotechnology based people were used to use empirical models of biomethane generation. Just fit the empirical models. There is other group of mathematically inclined people. They were developing really complex models of those microbial cells. So those models were useful, but those models required hundreds of net constants and parameters. Those were almost impossible to obtain. So these two classes of models were available in the state of the art. What we did was, borrowing from our chemical engineering expertise, we used our lumped reaction engineering models, and we could overcome the disadvantages of empirical models, and we could derive some benefits of detailed models like ADM1, but which required very few parameters, which can be easily obtained by doing some lab scale experiment. By combining these two aspects, novel design of cavitation devices and computational models, coupled with the experiments, lab scale as well as pilot scale experiments, we were able to in fact commercialize this hydrodynamic cavitation based pretreatment for enhancing valorization of biomass. And as I mentioned to you that this was licensed to a company called Vivera, I must declare the conflict of interest here. I am one of the co-founder of this Vivera Process Technologies, but I hope you allow me to talk further. I'm just showing you the results from some of the commercial implementation from Vivera. So this the first time we implemented this for a spent wash digester, and that brings this closer to the sugar, not just Indian sugar industries but global sugar industries, and we could convincingly establish that in commercial scale we implemented this to 50 meter cube per hour spent wash capacity, and in all these cases we could find from 14 to 22% enhancement in biogas yield, and that makes substantial impact on the productivity of anaerobic digestion. You can see here, traditionally anaerobic digestion had residence time of 4 weeks or 30 days or sometimes even more. With proper use of mathematical modeling and hydrodynamic pretreatment, you can in fact reduce that the HRT, the hydraulic residence time of this digester, so that not only you increase the yield per ton of feed, but you also increase the throughput for the same volume of the digester. And while though initial studies were for spent wash, we have extensively studied now use of this hydrodynamic cavitation for variety of biomass. And I'm showing you here example from our project with VSI, two major byproducts from sugar industries or side products from sugar industries, bagasse as well as pressed mud. Both of these we found substantial enhancement on biogas yield, right? So typical biomass from pressed mud, we could in fact raise it from say 100 meter cube per ton to 140 meter cube per ton. And same is true for bagasse. There again we could improve the biogas yield by 20 to 24%. Not just in lab scale, but we have also studied this in 50 meter cube with the help of VSI team here. This is the photograph of 50 meter cube digester, which this pilot tests were done at Nirabima sugar factory here nearby. Right? In all of these studies, we could actually show that this kind of simple down-to-earth pre-treatment coupled with simple modeling exercise can improve your productivity easily by 20+% for biogas. And we did couple of workshops here. This is the photograph from 2022 workshop here for sugar industries. At the end, I am going to ask questions to the audience before I close, right? So we conducted 2 such workshops, and we have extensive data on our effectiveness of our pre-treatment, not just the Napier grass, bagasse, pressed mud and so on. We also did that for different kinds of waste biomass. This was done for Irish dairy industry. As you know, dairy is one of the large industries in Ireland, and they generate lots of waste streams containing fat, soils and greases, FOBs we call. And we could again enhance that significantly. Professor Yadav also mentioned about macroalgae, and we also pre-treated macroalgae with hydrodynamic cavitation, and you can see here substantial enhancement of again biorefinery based on macroalgae. Not only you improve the biogas yield eventually of the residual algae, but you can also extract high value compounds from macroalgae much more effectively using hydrodynamic cavitation. Right? So I'm not giving you a lot of examples, just the point which I want to make here is relatively simple pre-treatment like hydrodynamic cavitation coupled with appropriate modeling can significantly improve can more than 20 to 25% improvement, lead to 25% improvement in your biogas yield. Therefore, bio-CNG and all other relating products. I'm just going to touch on two other intensification strategies which I think, which personally I am of the opinion that may work. One part is, again, in anaerobic digestion, you can improve the mass transfer, gas liquid mass transfer by injecting small bubbles. In anaerobic digestion, microbes will generate essentially CO2 and methane from the liquid phase, and these obviously these molecules, gas molecules, form at the cell surface. Unless you transport these molecules into gas phase in bubbles, the process is limited by gas liquid mass transfer, and you can improve that gas liquid mass transfer by injecting small bubbles. Now, how small those bubbles be? So we have done some experiments. So if you make the bubble size match closer to the microbe size, you get the maximum gas liquid mass transfer, right? If you inject just gas with few millimeter size bubbles, doesn't make any difference to effectiveness of mass transfer. So you need to create really nano size bubbles, which are bubble sizes are of the order of microbes. Then you can substantially increase gas liquid gas liquid mass transfer, and therefore methane yield. We have not yet tested this on pilot scale. All these results are still lab scale, but I personally feel that this can be scaled up. And again, here hydrodynamic cavitation can be used to generate those nano bubbles, because that highly localized shear which I mentioned about can break the bubbles and create those nano bubbles. Another part, again this part is more relevant probably to countries like Ireland, where plenty of wind electricity is available and hydrogen is readily available almost without a cost for us when the wind is surplus. In that case, you can inject that hydrogen to anaerobic digester, either directly in anaerobic digester or a bubble column followed by the digester, and you can then convert CO2 in biogas. As someone mentioned, that typical biogas composition is like 60% methane, 40% CO2. That CO2 you can convert it back to CH4. Again, that can go to other products like CNG and in this case, again, there are no pilot scale tests, but I believe that this is another area which one can look at and improve the conversion of biogas. One more part I have not mentioned so far. I have focused my talk on how to improve the yield and rate of digestion and yield of methane. I have not talked about anything about digestate. And that's one of the problem, right? So when you feed any biomass to anaerobic digestion, about 1/8 or 1/7 of that can be converted to gas, depending on how good pre-treatment you do. The rest of the material is going to come out from the digester as digestate, which is like a slurry, and it is important to figure it out. How do we add value to that slurry? Currently, that is typically used as composting and so on. There are 2-3 attractiveness for this AD business. India also imports a lot of fertilizer, or countries like India also import a lot of fertilizer. Most of that inorganic fertilizer can be recovered from digesting, and that is currently we are working on project. This is the project funded by Department of Agriculture and Forest of Ireland, DAFM, and we are trying to pre-treat and develop processes for digestate so that we can recover, first of all, liquid as well as solid fertilizers. And one of my colleagues in Queen's University, Belfast, is looking at photocatalytic transformation of some of the pre-treated digestate to hydrogen. So both of these currently are at the lab scale, but again I hope that as we make progress in the coming months, these will also be attractive areas for implementation. But even if you ignore for the moment these 2-3 ideas of intensification, digestate, valorization, as well as improving gas liquid mass transfer, rest of the discussion on pre-treatment and modeling can easily be implemented in practice even today. And my colleague Professor Yogendra Shastri from IIT Mumbai has done complete life cycle analysis of bagasse based as well as press mud based CNG for sugar industries. Like everyone talked about the low prices of electricity, there's no point in really using or wasting bagasse for cogeneration, generating low value product like electricity. It is much better if you convert that to say CNG as a liquid, as a transportation fuel, that can fetch you lot more value than selling the electricity back to the governments, right? We heard what our Gadkari said today on getting money and selling the electricity. Anyway, so without going into all of any of those, I want to highlight here that with this life cycle analysis, even with the old CNG price, this analysis when this was done, we had considered price of CNG as 46 rupees per kilo. So now prices have gone up significantly towards 70 rupees a kilo. I think this can really make sense, and that's where I really want to conclude and pose a question to you. So I just want to highlight here that this hydrodynamic cavitation, this novel hydrodynamic cavitation device which we have developed, coupled with comprehensive chemical engineering modeling, can really improve the productivity of anaerobic digesters. And we have been telling this, several papers have been published. We have conducted workshops at VSI. So before I answer your questions at the end of the session, I want to pose a question to you. Why sugar industries are not pursuing such a obvious case, so easy to implement? Many of the sugar industries already have anaerobic digestions. Why sugar industry is not aggressively pursuing CNG and all these intensification strategies to anaerobic digestion? So I hope at least some of you will answer me that question, and I'll close here. Thank you.